right, let's talk about heterogeneous equilibria, this term right along here. So let's say I drop a chunk of lead 2 chloride, this stuff right here. It's a solid and it's not particularly soluble. It's more soluble in warm water than cold, but it's going to start to dissociate. But it's a solid. When it dissociates, it spits out, for every 1 mole that dissociates, you'll get one lead 2 cation, and you'll get 2 chloride ions that will come apart. So this thing is literally coming apart into lead 2 cation and a couple of chloride ions in aqueous solution. And so that's going to turn over time, that's going to turn the solution to this sort of mustardy color in this depiction. All right, so the darker the color, the more the dissociation. But it's not incredibly soluble. It is more soluble in hot water. But in any case, when I write the equilibrium constant expression, I'm not going to include the solid because the solid doesn't change in concentration. The only thing that you include in the equilibrium constant expression, substances that can change in concentration. And that's going to be the lead 2 ion and the chloride ion in that solution. So it's difficult to define the concentration of a separated phase. In this case, the separated phase is a solid, but there are others. You need the density, so we just don't include it. And that is because principally the concentration of the separated phase never changes. Okay, as the number of moles of lead 2 chloride dissociate and make this lighter because you're losing grams of the solid, the volume depreciates. The volume decreases proportionately, and so the density is always the same. Then essentially that's the concentration. So we can therefore exclude the separated phase in the calculation of the equilibrium constant. So if I'm going to write the equilibrium constant expression for this dissociation, it's just going to be K is equal to the concentration of lead 2 plus times the concentration of chloride ion to the second power. This is chloride ion. I know it's hard to tell. But at any rate, this is my equilibrium constant expression. You can think of, but you do not need to include it in the denominator. You can think of the lead 2 chloride times, the lead 2 ion times the chloride ion squared over 1. But you don't really need to put that when it's in the denominator. So only gases and solutes are in dilute solution and included in the equilibrium constant. Those can change concentration. Gases can change in pressures, and aqueous solution, ions that are dissolved in aqueous solution, anything that's in an aqueous solution, can change in concentration. So what are we going to exclude? Pure solids, pure liquids. That includes water. Water is a pure liquid in these reactions, and so we don't include them. Solvents do not change in concentration, and water is a solvent in all of these reactions that we're doing. They don't change in concentration during reaction, but they still have to be there. So here is 3 lead plus ions. This is a redox reaction, just to remind you. We've got a 0 oxidation state here, a +1 oxidation state here, 0 here, a +3 oxidation state here. And so silver is being reduced to silver metal, and iron is being oxidized to iron 3+. Okay, and so a matter of 3 electrons are being transferred in this reaction. But the only things that change concentration are silver ion and the iron 3+ ion, which is our product, our only product. and it's got a coefficient of 1, so it gets a 1 as an exponent. Silver ion has a 3, it gets a 3. We omit the solids when we write this expression. Okay, try and remember. So quiz, equilibrium constant. Here's calcium hydroxide solid. It's going to dissociate in solution. Remember, this is a solid. Are solids going to be in the equilibrium constant expression? Okay, here are the products. How do we write equilibrium constant expressions? If you remember, it's products over reactants. Okay. Here's another one. What is the equilibrium constant expression for the following reaction? We've got 1/8 of a sulfur 8 solid. This is a solid. Now this is a gas phase reaction, and gases are included in the equilibrium constant expression. Here are your products. Here is your reactant. Okay? And there we go.